Hello students, in this video we will study the behavior of magnetic dipole when placed in a uniform magnetic field. But before going ahead, you must watch my previous videos of this chapter, Magnetism and Matter, to understand this topic in a better way. Also, you must be aware of electrostatic analog of magnetism. See here, the magnetic dipole or the bar magnet is placed in a uniform magnetic field. This magnetic field is generated externally. You can suspend the magnetic dipole by a thread. In presence of the external magnetic field, a force is exerted on north pole as well as on south pole. Due to this force, a torque is formed and it will try to align this dipole according to the external magnetic field like this. Now let us start. For this we have considered a bar magnet of length 2L having magnetic dipole moment M, moment of inertia I, and it is placed in a uniform magnetic field B at an angle theta with the direction of the field, and it is allowed to oscillate in the magnetic field like this. See here, this is the bar magnet having length 2L. Force is exerted on the north as well as on the south pole, that I have just told you. Due to this force, a torque is developed. The deflecting torque on the dipole is mb sin theta. If you remember, when we have studied the electric dipole placed in a uniform electric field like this, consisting of two charges minus q and plus q, and let this be the direction of the electric field. This is the way which you have studied in chapter number 1. From here you have calculated the torque as Pe sin theta. By analogy also we can calculate this deflecting torque, that is, the analog of electric dipole is magnetic dipole, analog of electric field is magnetic field, and then sin theta. So we have calculated the torque in magnetic acting on the magnetic dipole, which is mb sin theta. Or you can calculate in the same way as you have done to calculate Pe sin theta. That is, we know the formula torque is equal to force into perpendicular distance. The force can be written as pole strength multiplied by magnetic field, and the perpendicular distance we can see from our figure. See here, the perpendicular distance is 2L sin theta, so that we can keep it here 2L sin theta. If we combine this 2L and pole strength together, it will form magnetic dipole moment into magnetic field for this and sin theta. So this deflecting torque we can obtain either from the analogy or directly from this formula, force into perpendicular distance. But whenever there is a deflecting torque, definitely there will be some restoring torque also, which will be in opposite direction to this deflecting torque. That is a restoring torque, which will have the same magnitude mb sin theta, but its direction will be opposite to the direction of the deflecting torque, because its function is to oppose the deflecting torque. So we will put a negative sign with it. Also we are aware torque is equal to I alpha. We know in linear motion force is equal to mass into acceleration. The analog of force in rotational motion is torque. Analog of mass in rotational motion is moment of inertia, and for linear acceleration we can write down angular acceleration that we have written here I alpha. We can even write this angular acceleration as second derivative of the deflection, that is d2 theta upon dt square. Rearranging this term, that is, we have kept this torque value I alpha in the above equation of restoring torque, which is equal to minus mb sine theta. So we have obtained this expression. For small angles, we can even write sine theta as only theta. But if you look carefully, this is the equation for simple harmonic motion. So we can compare it with the standard simple harmonic equation, which is this. That is, alpha is equal to minus omega square theta. If we compare this with our expression obtained, we will find omega square is equal to mb upon I. And we know that the time period is equal to 2 pi by omega. So I have put down this omega value here, and I have obtained time period as 2 pi into under root I upon mb. We can rearrange this expression and we will obtain the magnetic field exerted on the dipole when placed in a uniform magnetic field, which is 4 pi square into I upon mt square. And we are aware that omega is the angular frequency in radians per second and t is the time period in seconds. Now, let us calculate magnetic potential energy of the dipole when it is placed in a uniform magnetic field. We have just studied that when the dipole is acted on by external magnetic field, a torque acts on it, which will try to align that dipole according to the external magnetic field. Definitely some work is done to change the orientation of the magnet against the torque. So, potential energy of the magnetic dipole in a uniform magnetic field is the energy possessed by the dipole due to its position in the field. This we know. Magnetic potential energy can be calculated in the same way as we have done in electrostatics. So, let magnet be rotated through a small angle d theta against the torque. So some work is done, and this work done is stored as potential energy of the magnet. So potential energy will be equal to integral of torque d theta. Let us put the value of the torque we have just calculated, which is mb sine theta into d theta. Integrating it, we will obtain minus mb cos theta, or even in vector notation we can write down the dot product of m and b. There can be few special cases, like when theta is equal to 90 degrees, the potential energy will be 0, and when theta is equal to 0, the potential energy will be minimum, which is the most stable position. This you can understand it in this manner, that when the dipole is placed in a magnetic field, suppose this is the external magnetic field direction, that means this is the north pole of the external field and this is the south pole of the external magnetic field. So we are aware that we have angle theta between the magnetic axis and the magnetic field. Now when this angle theta is 0, then this dipole will align itself according to the magnetic field, that is in this way. So what does it mean? This is the direction of the external magnetic field and our dipole is aligned at an angle theta. That means the north pole of the dipole is towards the south pole of the external magnetic field and the south pole of the dipole is towards the north pole of the external magnetic field. Hence, this is the most stable position. And when theta is equal to 180 degrees, that is the potential energy is maximum, which is mb, and it will be the most unstable position. That we can understand it from this figure only. Now let us attempt one numerical. A bar magnet, when suspended horizontally and perpendicular to the Earth's magnetic field, experiences a torque which is equal to 3 into 10 raised to the power minus 4 Newton meter. What is the magnetic moment of the magnet? That means we have to calculate m. And here the magnetic field of Earth at that place is given as 0.4 into 10 raised to the power minus 4 Tesla. We are aware the formula of the torque, which is equal to mb sin theta. Rearranging it to obtain magnetic moment and putting down all the values given in the question like this. So we will obtain magnetic dipole moment as 7.5 joules per Tesla. Thanks for watching. Please like, share and subscribe.